So this is Pascal's principle, which says when a change in pressure is applied to an enclosed fluid, the change in pressure is transmitted to all parts of the fluid and to the walls of the container. And so this is just a simple sort of example of that. This is a container that's closed, and just to make things simple, we'll say the pressure above the fluid is 0, so we're not worried about the gauge pressure, the atmospheric pressure, right? And then we could say the pressure at the bottom is what we've already decided, PB is equal to just as I wrote up there, rho GH, right, where H is the height of the fluid. And now we can say, well, what if we put a piston above this thing that's just got a certain mass M, right? And so now it's just sitting on top of the fluid, right? Well, now the pressure at the top of the fluid is equal to mg divided by the area, right? Where A equals the area of the fluid at the top, right? If that's a cylinder or something like that that's sitting on top. And that means P bottom is just P top plus rho GH. Or in fact, at any height, this is the pressure here. If this is H over 2, then the pressure there is equal to P top plus rho G H over 2, and so on. The pressure at every point is increased by the amount of additional force that was added to the fluid at the top. So we're going to show how this is sort of an underlying principle of hydraulics. It's how when you take your car to the mechanic, they can raise your whole car up with a piston. And I'll give you an example of that next. So here's the idea. This is how hydraulic systems use Pascal's principle. If I have a fluid, right, and I have a piston here and a piston here, and this one's big enough to hold your car. This is a little silly because actually the pistons are smaller than the car and they sit underneath it, but just for illustration we draw it this way. This is a fluid inside that's connected between the place where I'm applying my force and the place that's getting the force in return. Hydraulic systems are often called fluid equivalents of levers. And so the idea is if I put a force this way, it increases the pressure at this point, right? But in a fluid, if they're at the same height, then the pressure at this point is the same as the pressure at this point. And so the pressure at 1 is just the force I apply divided by the area at 1. And the pressure at 2 is equal to the force that gets applied divided by the area at 2. And since those two pressures are the same, F1 over A1 is equal to F2 over A2. And that means that F2 is F1 times A2 over A1. And so the force that I get on this side is the force that I apply on this side multiplied by the ratio of the areas. So if I have a really big area here compared to here, if this area is 100 times bigger than this area, then I get 100 times the force. The catch to this, you might think, well, aren't you getting something for nothing? The catch is, of course, is the smaller this gets, the farther I have to move this plunger to get an equal rise on this side, because it takes more fluid to make this move up an equivalent height to this one. And so usually they have a motor that's pressurized that's moving the fluid in as it's filling it up, but under a pressure that allows it to lift this other side. And so so this is the formula. So if you make 100 times an area, you get 100 times the force. It's very similar to a lever, where if the length of a lever, if I have a really long lever arm and here's my fulcrum, if this side is 100 times longer than this side, I get 100 times the force. This one would have to move 100 times as far, and so that's the trade-off you get. But you get to get a very large force from a very small force as long as you're willing to let it move slowly. Most cars use hydraulic brakes. The pedal acts as a lever. When you press your foot on the pedal, that's actually a lever that's applying a force to a master cylinder. It's the small cylinder that we apply the force to. That's called the master cylinder in your car. This force is then transmitted to the wheels by a hydraulic system, as we talked about in the last example. So in this example, a 100 Newton force on the pedal is converted by the pedal lever to a 500 Newton force on the master cylinder. What is the force at the four wheels if the radius of the master cylinder is 0.5 centimeters and the radius of the slave cylinder, the ones at the wheels, is 2.5 centimeters, right? And so what we said last time is, look, the force that you're applying, the force that you're getting, F2, this is at the, so I'll write it this way, I'll say the force at the wheels is equal to the force at the master cylinder times the area of the slave cylinder divided by the area of the master cylinder, right? And so that gives me the force at the master cylinder is 500 newtons. And this is the area of the slave cylinder is pi times r slave squared, and that's divided by the area of the master cylinder, which is pi times r, the master cylinder squared. And this is, I've got my 500 in there too quickly, but the pi's cancel, right? And this just gives me r slave cylinder over r master cylinder squared, right? But the slave is 2.5 centimeters and the master is 0.5 centimeters, so that's a 5. So it's 500 newtons times 5 squared, which is 25. Right, and so 25 times 5 is 12500 newtons, 12,500 newtons, maybe 300 pounds or something like that. 3,000 pounds, that's better. Yeah, so a small 100 Newton force, 100 Newton force is maybe 25 pounds. That you apply with your foot gives you thousands of pounds at the wheel. And the catch is the brake is so close to the wheel that it only has to move a tiny distance, and you get to apply that enormous force to your wheel, and that's how you stop a car with just by a gentle pressure from your foot.